it's very fitting that we have this workshop continue the effort in this building, the Center for Computational Technology, because it's very important to what we do for engineering, as well as what we do across the board for everything relating to computations. So thank you for being here, and I hope you have a very productive conference. And I think our very hardworking dean of engineering is next. Thank you so much. Thank you.
I just wanted to stop by and welcome you on behalf of LSU and the College of Engineering. I want to let you know how excited I am about having this event here today. So it was about probably 2 or 3 years ago that Dr. Nandakumar and Mark Tyagi visited with me, and we went to lunch at the faculty club, and they said, we have an idea. Wouldn't it be cool if we were able to gather all the power that we have in computation and process improvement and couple that to support the industries that drive Louisiana's economy? And we're thinking about this idea of something called EPICS and creating a center to be able to generate and spin off our technologies and help our industries. And I knew at the time that because those two guys were going to lead it, that it would be a success. But I knew it would be a great success because of why they were doing it. The reason they were doing it was not just to generate more journal articles and get more research papers. Well, that will happen, and get more funding. The real intent was to help drive the success of the businesses that are here in our state and our region, so that this would be the place for people to come and establish their companies. And so I think what you're seeing today, we're now using the word consortium. If you look at the logo, all of the entities that they support through this initiative, if you look at the group and the national and international group that he's had working with us for the last 2 or 3 years, it's happening. So for me, seeing this event, this third event, is really a flag going up that the dream that those two guys had back 2 or 3 years ago is coming to reality. The fact that half of this whole program is populated with people from industry talking about their needs, that's our vision, and that's what we want to do in the College of Engineering at LSU. So this is a great exemplar for what we encourage all our faculty to do in the College of Engineering. So thank you very much, Mark and Nandakumar, for organizing this and having a vision to make this a reality. Thanks so much.
Thank you, I think without his support, we would have started this 2 years ago. He was very generous. We told him what he needed, and he immediately made all those things possible for us and continues to support us. So we are very optimistic that in a few years' time we will have an Institute for Process Innovation on the LSU campus. It makes sense, and hopefully throughout the day you will see the reason for that case and that vision and the passion that all the faculty here share with us. The next person I would like to welcome is Dan Boone, the Arts Directors, and the brain behind the Louisiana Chemical Association. We'd like to hear welcome
I love microphones, so I think I'm going to stand behind here. I'm Dan Bourne, and I work for the Louisiana Chemical Association. The Chemical Association consists of, now, as of this instant, 64 multinational chemical manufacturers who operate at 108 locations in Louisiana. We are growing, and we're growing at a rate we never dreamed of just a few years ago. Because from 1999 to 2009, we shrank from 75 companies to 61 companies. We shrank in locations from 105 locations to 95 locations. And we were shipping jobs overseas at a remarkable rate and closing down major manufacturing facilities in Louisiana. And then the magic of innovation, the magic of let's find a better way to do it, showed that natural gas fracking could completely turn on its head the economic model that we thought would prevail for years to come. And so because of natural gas, which is the daily bread of our industry, we are now on a growth surge. And so our employees at our plants have gone from 24,000 at our lowest back to 29,000 organically from companies that are already here. companies that are coming are now growing $20 billion, that's with a B, $20 billion worth of investment that's coming out of the ground as I speak. And there's another $20 billion of investment that's on the books that we think we'll get at least 70 to 80% of. So that's about $40 billion in the chemical industry at all, that alone. That doesn't count the refineries. That doesn't count the offshore activity. Doesn't count gas to liquids. Doesn't count lots of other investments that are being made, including LNG. And so I think we can all appreciate the power of the investment that is coming here. And I think we can also predict the power that what you will hear about today will add to that investment and will add to the efficiency of those operations. I have to say, I was very impressed, Rick, over the last 6 weeks at an effort that began here at LSU and has morphed into a partnership of over 80 public and private entities, making a formal application to the United States Department of Commerce to have South Louisiana designated as a manufacturing community. This is huge if we get this. It's going to send research dollars and it's going to send dollars to build stuff to Louisiana in a way that we've never experienced. And there are 6 areas that are going to be affected. 1, research and innovation. How about that? Workforce training, infrastructure and site development, supply networking, trade and international investment, and operational improvement and capital access. I have to say the efforts that College of Engineering and its related departments put forth in organizing and bringing forth this consortium, this application, was the best example I've ever seen in 40 years of working in this industry, of industry and universities and other public entities coming together to be on the same page and to move forward this incredible manufacturing engine that we know as Louisiana. In 2012, Louisiana plants shipped $68 billion worth of stuff. That's $10 billion more than we shipped in 2010. That means that in 2 years, coming out of the recession, we increased our output $10 billion. That is just a metaphor for the growth that's going to come to this state. And so we're very excited about what this university does. We're very excited about teaming up with the university when we can to move our industry forward. We are still the 3rd largest chemical manufacturing state in the nation. We're right behind California. King Alexander tells me that California is 2nd because it counts marijuana as a chemical. Texas is 1st. We'll never catch it. But then who would want it? Who would want to? We're positioned now as we've never been in Louisiana to grow this industry. And it is the work that you all do here that will help us be the most competitive we can be for the next century of growth. Thank you very much, and have a great, great conference.
Thank you for those inspiring words. And I guess a few announcements before we get into the technical part. This is a very high-tech room, and apparently there are 40, 50 mics. So it will pick up everybody, so people can speak without a mic from here. If you also whisper to your neighbor, you also be picked up. And another announcement, I guess, is there is no food allowed in here because there are electrical outlets on every chair. So if you want to connect your computer or something, you can do that. But because of that hazard, there's no food allowed inside. Now we get into address one of the often challenging tasks when university and industry get together to do something good for the common good, and that is the intellectual property issue. Who owns what and how do we share these? And I'm very pleased to introduce Mr. Andrew Mass, who is both an engineer and a lawyer, who understands both sides of it, and has been helping EPIC in tremendous ways over the last year to frame some of the documents. So if you picked up these folders, you will find inside the documents for the consortium that lays out our vision of how we want to develop this relationship. So thank you, please.
Good, Dr. Nandakumar. Thanks for having me. Just by way of introduction, my name is Andy Moss. I'm the Director of the Office of Innovation and Technology Commercialization here at LSU. I've only been here for about 9 months, and I come from the chemical facilities of the north in Ohio. I saw there were a couple people here from Ohio, where I worked at the University of Akron, where we were very heavily involved in consortia like this that were focused on the polymer industry, especially chemicals, and I believe that this is a great opportunity for Louisiana. One of my loves is helping focus on economic development in a region. And if you look at the reports and the data, it suggests that every booming economic development center in the U.S. is centered around a high-caliber research institution. And we have the high-caliber research institution here at LSU. And one of the reasons I came here was because I saw great potential. I saw this huge potential for LSU to thrive and for the region to thrive in the partnerships that we can forge through LSU and industry. Many of you, I don't see him here, many of you know Tom Ura at BASF. I did my graduate work at UT Austin. His dad taught at UT Austin, so his dad was one of my faculty members when I was in graduate school. And so he grew up in Austin. And he and I chatted one day, and he indicated that he felt like Baton Rouge was in the position that Austin was in 25 years ago. And I think about that, and I think this is an awesome opportunity we have here. Because if you look at everybody in the world now points to Austin as this great, burgeoning economic development area that's focused on technology commercialization, startup, collaboration, industry, university collaborations. It's just one of those places that a lot of people are trying to emulate. And I think that that's something that Baton Rouge can become. So as Dr. Nandakumar said, I am an engineer. I'm a civil engineer. So when it comes to a lot of the things you guys do in industry, I understand them. But then for some reason, I went to the dark side, so all you engineers are hearing, I did go to the dark side. I went to law school, became a lawyer, and now work specifically in the assessment and evaluation of early stage technologies. A couple things that I wanted to touch on really that I've really been focusing on here at LSU since I've gotten here. The first one is that we're trying to affect the culture of within LSU, but also external to LSU, so that industry recognizes that we are here to play in the game. In the past, it's been really hard, from what I understand, that industry would show up and say, we really want to collaborate, we want to work with you, but it just became so cumbersome. And you probably got, if you tried that in the past, you probably got things like the bylaws of the university, put in your face saying, we can't do it because of this and this and this and this. And I recognize that the bylaws are cumbersome, and LSU has there's some issues there, and we're working through those. But my job, with respect to the collaboration with the industry, is to figure out ways to navigate through those bylaws with you, industry. I'm working really hard to engage with the business community. If you haven't received it, we are having an inventorship showcase on May 19th at Lod Cook. It's free to attend. It's been very well sponsored by industry collaborators that see the value of having technologies that are developed at LSU showcased for industry to see and to understand what's going on. The other thing that I really like to focus on is what I call wealth creation. And you can call it value creation, wealth creation. And it's not wealth creation for LSU. It's wealth creation for the greater community. Because if we're able to assist in some way in a business, a company, industry partner to be successful, and they're going to build wealth. They're going to build local wealth. And that local wealth is going to benefit all of us. It's going to benefit the university community. It's going to benefit LSU. It's going to benefit Louisiana. It's going to benefit Baton Rouge. I mean, it's going to benefit everybody that's a player in there. And so one of the perspectives I take a lot when it comes to industry collaboration is yes, I have a mandate to try to maximize royalties, but I'm also looking at the bigger picture of this is a bigger picture relationship. We need to build these relationships so that when it comes time to see those relationships flourish, we're able to help and assist in that process. And as Gus said earlier, LSU is open for business. We believe that there's a lot of tools, facilities, and knowledge that is here at LSU that could and is valuable and important to industry partners here in the region and abroad. Like I said, if the businesses in the region succeed, then LSU will succeed. And ultimately, when it comes down to it, we invite you as the industry partners to engage with our faculty. Engage with our faculty, start to discuss your problems, and I know that's sometimes scary, but talking about your problems with our faculty members allows them to realize what they need to be doing to solve real-world problems. So often I have a faculty member come into my office and come to me with his intellectual property, which is great, and I love that. They then tell me what it's used for. And what it's useful for, and I say, well, who have you talked to? Oh, I haven't talked to anybody about it yet. Well, how do you know that's what it fixes? Well, just because I know that everybody has this problem. How do you know everybody has that problem? Well, I just think I know everybody has that problem. Well, who do you think has this problem? And they'll say things like, and I'll pick on Albemarle because I know they're here. They'll say, well, I know that Albemarle has this problem. Well, have you talked to people at Albemarle? Well, they mentioned it in passing. Well, have you talked about the details of it with Albemarle? Well, no, I don't want to give them my idea. I don't want to give away my idea. And I carefully coach them and say, look, talking to them about your outcomes doesn't give away your intellectual property. If you talk to them about the way you get it, the how, not the what, then we might have some issues. And if you're getting to the point where you're wanting to talk about the how, we can enter into a confidentiality agreement. We're working on a master confidentiality agreement with Albemarle right now. But again, it's one of those things where I want to help our faculty engage with industry so that our faculty are really solving your problems, because that's critical here. I'm open for questions. If there's anybody that would like to connect with me, let me know. The EPIC consortium agreement in here, we've worked really hard to put that together in a way that it's meaningful to all levels of industrial partners, not just the big players. It was modeled after some things that I did up at Exxon with a big consortium that was started by Exxon. So there are some things in there that I think are meaningful across the board. So again, if you have questions or concerns, let me know. Let Dr. Nandakumar know, and we look forward to partnering with you. Thank you.
With those inspiring remarks and visionary leadership from LSU President, LSU President, and the right environment that everybody is creating, I think we can really succeed in our mission. What is our mission as an educational institution? It is to train the next generation of students to be leading thinkers, innovators, and to engage the industry to solve practical problems instead of made-up academic problems that we do normally in PhD thesis. So that's what it is about. So next about 30 minutes or so, I'll take to share our vision of the specific details of what we intend to do within and how we hope to engage the industry and the faculty not only in LSU but around the nation, in fact around the world, in this vision and in this talk. Let me take a few minutes to talk about this logo. As we were designing this logo, we kind of asked people, what do you see in it? The logo should be able to convey all the meanings that we intended to convey. But interestingly, it does generate a lot of imagery. Some people saw a cross in this. We are from Eastern Europe, I guess, and others from India saw some sort of a glory kind of a pattern. But what we intended to put in this one was things that are plenty in Louisiana. Sun, we have plenty of sun, we have plenty of water, and everything grows down. Okay? And we also have plenty of fossil fuels. And we take those and feed our chemical plants. We have abundance of all of these things. And our goal and EPIC mission would be to improve the current processes that are used in the plants. There are over 300 chemical plants along the Mississippi River that are based on fossil fuels, for example, as a raw material. But blend that with renewable material that plants grow very well in Louisiana. So make them as the feedstock to feed our chemical plants. And we can have a thriving, very innovative industrial concept in Louisiana with LSU spearheading the Process Innovation Institute. And you also see the LSU colors, and you see the two infinite signs, which represent the sustainability. So we need to go away from fossil fuel dependence into dependence on the renewable fuels to have a sustainable technological development, sustainable economy, etc. So we need to teach our students in all these. So the EPIC program actually has several aspects to it. Training aspect is a strong one, research aspect and innovation aspect is a strong one, and linking people together to come together and share a problem, set targeted goals to solve specific problems. So there are a lot of initiatives that are being we are working on, planned for the next 2 years. I will share them with you as well. So this is our vision of what EPIC should address. So it's a bit of a technical picture. So what we see is there are two fundamental bases on which we want to build. One focuses on what we call 3M, multi-scale, multi-phase, and multi-physics. Those in the chemical plants will really experience this on a day-to-day basis. Most of the chemical process units, we have multi-phases, gas, liquid, gas, solid, liquid, solid, combinations of this. So we need to understand the physics of it in rigorous detail so that we can develop simulations. Once we have simulation tools using high-power computing, we can then explore larger design space. So we want to move away from traditional empiricism-based design approaches in chemical industry to approach that depends more on fundamentals, more on advanced simulations, advanced measurements. And in this third workshop, we have expanded the scope to 1 day, and we have added a lot of new features to it. There will be a poster presentation at noon around lunchtime, and EPIC graduate students will showcase what the range of problems that they are working on. Some of them are industrially inspired. And then we have in the afternoon added a section where industrial people will come and present the challenges and opportunities that they see for process innovation. So by putting all these things together, mostly in academic environment, but with input from industry, we develop advanced simulators. And these simulators, there are a number of them already in existence, and new ones will be created to add additional features. But they must be validated against experiments before they can be used and trusted for design, advanced process design. So the other leg is the enabling technologies, what we call the enabling technologies, which is advanced measurements. You will see at LSU we have fantastic facilities, tomography-based techniques, and the CAN-D facility for synchrotron-based measurement techniques. So we can probe all the way from the molecular scale to large-scale equipment to get the data. That the data will then validate our models. And we also have the capabilities for advanced measurements, manufacturing. Okay? So I think Dan talked about the manufacturing, getting LSU in Louisiana declared as a manufacturing hub in the chemical space. So by combining these advanced simulations, which come from this unit, with advanced measurement, advanced manufacturing, gives us the enabling technologies to dream and think and design newer processes, more efficient processes, with a smaller carbon footprint, etc. So throughout the talk today, we have scheduled it in such a way that you will see a glimpse of what is happening in bioprocessing industry, what is happening in computational industry, what are the tools that are available at LSU and at our partner institutes around the nation. So by combining these two, what we would like to do, in collaboration with university, industry, and national labs, we would like to build an EPIC consortium. Initially, I guess it will be focused around the Louisiana area, but our larger vision is there will be an institute here, but there will be satellites all over the globe working together to solve problems, exchanging people, exchanging ideas, etc. That will produce workforce that is well trained to think in terms of innovative designs for the future, and will help the chemical manufacturing industry. So it will help in advancing the research aspect. So this is the kind of picture that we have. So there's a strong training element for training the next generation of graduate students in this innovative design processes. I have to keep the time for me and keep talking about it. So the EPIC goals specifically are to address industrially relevant research. So we want our graduate theses to be inspired and focused from industrially relevant problems, but going into a space where we are looking at the fundamentals so that we strengthen our fundamental understanding that enables us to design novel designs. And you will see a few examples in the poster as well, designs based on fractal distributors for bubble column design. Advancing the fundamental knowledge itself, developing experimentally validated with high fidelity experimental measurements, simulation tools, and leveraging the advances in computing, measurement, and manufacturing for process innovation. So this is a major goal, to develop an industrial common. Just like Silicon Valley is the hotbed of innovation in the area of information technologies, computers, and communication technologies, Louisiana can be that with the chemical industry if we can develop the right environment and foster this development. So an industrial commons in the chemical and energy sector that combines both traditional energy and renewable energy. And develop environmentally sustainable. Sustainability is also a key feature in our goals. And train the next generation of skilled workforce. The opportunities, of course, are along the Mississippi River. There are over 300 plants in Louisiana alone. So if we can get them to engage and support the formation of an institute or a consortium, I think we are well on our way to realizing this goal of the dream. So this is another way of looking at it, the fundamental science at the bedrock of innovation and enabling technologies at the next level, which feeds information. So there are loops everywhere, there are iterative cycles. We want to try and iterate on concepts without fear of failing. And if we fail, we just throw away that idea, but take new ideas and keep moving forward. And at the top of this is the innovation engine that we envision, where we will have a chief innovation officer for a consortium or EPIC institute, and interacting with industries, pushing out ideas to industry, getting back their problems, and a loop there that continues to innovate. And then, of course, feeding back information that has to be generated at the fundamental level as well, also on the enabling technologies level. So this kind of investment then helps us to be continuously innovating in this space with new processes, improving existing processes. So in terms of bringing the people together, we have this vision of, we started, as the dean said, 2 years ago with very limited funding with an EPIC seminar series. So we have brought in about 25 world-renowned scholars from all over the world, Europe and US, from national labs, from industry. And this has had multiple effects. Of course, we talk to them about EPIC and everybody gets excited about the idea, see how we can work together. And it inspires our graduate students to see distinguished people come and interact with them. So it increases our productivity as well. So the question is, how do we scale this up? How do we bring all the graduate students working on similar areas, and cyberspace allows us to interact like that. So we need to find mechanisms for sharing these kinds of things on a national and global scale. But we started with that small scale, and then we started developing domestic partners in the sense we put together an attempt at an ERC with NSF, and we worked with Iowa State, University of Florida, Texas A&M, and our contacts keep increasing, and hopefully we will work together at the next attempt to realize an ERC somewhere in the nation, but focus on this area. And of course, we have international partners as well. We have Professor Ali Al-Manzouri from the Petroleum Institute, from UAE. We have contacts, collaborations with people in Singapore, in Canada, in France, in UK, etc. And of course, chemical industry. We need to bring the chemical industry into this picture so that we have active exchange of graduate students and faculty and people from industry spending 3 months at the institute, for example, for process innovation. So that's our vision. So this is our vision for graduate education. How do we impact graduate education? In fact, we are currently putting together a proposal to NSF. So essentially, we take fresh graduate students and we take problems from chemical industry and go through a series of courses and work experience in plants, in relevant places that will produce a graduate who is able to do process innovation, and that will result in cleaner chemical plants. But in the process, we need a lot of things need to happen. And we are particularly seeking help from our international academic partners as well as industrial partners for internship opportunities for our graduate students. To spend 3 months in a plant, for example, or to spend 3 months in Imperial College with our colleagues working there on research. So that kind of an exchange will allow us to collaborate and exchange ideas and increase the rate of progress. So this basically details all the course details of how we will achieve this training element for the graduate students. And this is a consortium. In fact, this is our primary goal at this workshop. We want to launch a campaign for industrial consortium. So this is one model that Andy has helped us a lot to build over the last year or so. Andy and his office have put the documents together. So in the folder, you will see the consortium documents. Please take this and discuss it with your companies, organizations, and help us by joining the consortium. Our goal is within a year, we want to bring about 10 members in, and over 2 years, about 20, 25 members, and then grow this beyond into an institute. So there are 3 days of membership that we have identified, 45,000, 30,000, and 50,000 annually, depending on the size of the company. But the key differentiators of this consortium document, which took us a while to figure out internally, from any other standard consortium document are the following. Particularly one key element, that there is an aspect where we want to create an environment where we interact with you much more closely. It's not like you sign a check for 45,000 and you come and attend an annual meeting like this once a year and you get a report and you file it away. So we want this to be beyond that. A lot of academic consortiums exist in that model, in big universities, in fact. So one of the key aspects of our consortium is that we have a member-dedicated project. And what it means is for $45,000 that you pay as your membership fee, there are certain benefits, like attending a workshop, attending short courses for free, and picking our brains, having 2 or 3 meetings a year, etc. And those are standard without really much significant consequence. But the member-dedicated project has very significant and profound consequences, I think. And essentially what we are promising to do is deploy 3 months of our time, one of our research associate time, to work with you on one of the problems that you would be interested in solving in your plan, underprotected intellectual property issues. So you can look at those documents in the folder, and if there are concerns, of course, you can bring it back. And but we would like that a lot of thought has gone into that, so it is supposed to be fairly robust and generic to address our main concerns. And at different levels of membership, that will be the variable. So if you join at 30,000, then you get 2 months of our time. And in that time, we actually work on a problem that is shared only with you, and that addresses a problem that you are interested in knowing more about. In addition to that, of course, the rest of the problem money goes to that. The rest of the money goes to support the general consortium agenda. So there will be a consortium advisory committee that will pick the leading projects that are at the fundamental level that we need to understand, and it will advance by funding PhD students. Initially at LSU, but as this grows and other universities join this concept and develop their own consortium in place, we can then exchange these funds wherever the expertise is. And I think that's one of the ways to rapidly achieve innovation. And also, please feel free to ask and stop and ask any questions, particularly people from industry. If you have concerns or questions, you can ask me now or at the breaks. We should continue to engage after the workshop is over and now. So what have we done in the past? As I said, we have done the Epic Seminar Series that has been running well, and the third year it will be starting this fall, and we've already scheduled 6 presentations a term, roughly. And we have conducted a number of Epic workshops as part of AACHE meeting, as a part of CACHE meeting, and this December we have one in Indian Institution of Chemical Engineers in Guwahati. So anybody is interested in going to India for an opportunity, this will be a good opportunity. We will have an Epic symposium there that you can participate in and travel as well. India is an exciting place these days in terms of economic growth and activity. And we would like to have Epic visiting professorships. We have had a few. Our resources right now are very limited. Professor Joshi comes here and spends a week once or twice a year, and we have had Professor Miller, a number of others come. And Epic Consortium is the one that we are currently working on that we have to push that agenda forward. So 4 of us started this about 2 years ago, as the dean said, and we have been expanding our faculty strength within the LSU. We are putting together a whole range of expertise that would be needed to address the problem of this fact. People who have experimental strength, people who have computational strength, fundamental physics and modeling strength, etc. We're all coming together to advance this cause. And external partners, as I said, University of Florida, the Institute, and that group is also expanding. So let me switch the gear to a little bit of technical reasons for this process innovation and the path that we are proposing, how we will achieve this vision that I laid out. So what you see here is in the automotive industry, from a Model T to a modern Porsche, there has been tremendous improvement in the technology. And this is the invention, and this is according to Bob Holzer from Dow, Chief Technology Officer, who gave this kind of a distinction between invention and innovation. Invention is something that you create that doesn't exist. Innovation is something that you continue to improve on incrementally, and over a period of time, it results in substantial improvement. And if you look at the aeronautical industry, from Wright Brothers planes to a modern Dreamliner, again, a tremendous improvement. And I don't know how many of you recognize what this is. This is the first ENIAC computer, a room full of machines, and this is your cell phone that you all hold in your hand, which is probably 1 million times faster than this. Okay. Again, an innovation in the information and communication technology that has occurred through sustained, continuous innovation. And if you ask the question, what is the process industry status? A 1940 chemical plant, the distillation column, a 2000 distillation column might look like that. Internally, essentially, it's essentially the same thing. There have been innovations in the products that chemists have synthesized and that we have chemical engineers have produced in large quantities. So new products have come into place, but the way that we process has not seen a lot of innovation, and that is our thesis. That's what we want to change. There are probably about 400 different types of chemical equipment, and you can use this in many combinations to achieve your goal of taking the raw material, producing a product that you want. So the question is, can we innovate those? Can we make them more efficient? Can we make the carbon footprint smaller? And the question then you ask is, why has there not been significant innovation? And the answer to that is the complexity of the process itself. And we are at a threshold where we can address these complexities and enable process innovation. So what you see here is inside the distillation column that I showed you, the vapor-liquid track at three different regimes. And you see that there are vapors and liquids contacting, flowing concurrently. And it is a tremendous challenge to understand the dynamics of what happens here. And the separation efficiency of a distillation column depends profoundly on this. So how do we currently design? We have this McKay-Thiel kind of a method where there are efficiencies. We ignore everything about the fluid mechanics. We assume that the fluid mechanics is homogeneous. So we divide the flow regime into different regimes, and we know by experiment from the bench scale to the pilot scale that this is the ideal regime to operate on, cloth regime. And so we adjust our operating conditions to be in this domain. And we assume that everything is homogeneous in that domain. So if you take a sample of your distillation column, for example, a atmospheric crude column, sample from one corner or another corner, we assume that the composition is the same. But in a car that has a diameter of 10, 15, or 20 feet, you will see that that is not the case. The mixing here is profoundly going to affect the separation of the two species. And they're all governed by the same set of equations, Newton's law of motion, conservation laws. Okay, so the challenge is in our inability to solve this. These are very complicated models. But with computers, we can actually unpack the secret in these models, in fluid mechanics. So we don't have to make those assumptions anymore. That's the first stage. The second stage is that what is happening in the innovation of manufacturing allows us to rethink whether this is the ideal configuration for a distillation column, or should we redesign a completely different way so that we can achieve a smaller equipment achieving the same separation. And we have examples, I think, this afternoon on a technology called hydroflame, where you have a very small device that can produce steam in very large quantities. A very clever example of process innovation. So this is an example of how we typically, for the last 100 years, been designing distillation columns. A method that was developed in MIT called the steel method. Chemical engineers will be very familiar with that. And there are a lot of assumptions that go into it. In the 80s, some of these assumptions were removed with the advent of computers and with the advent of simulators like Aspen and HYSYS. They look at the whole equipment. They don't look at what happens inside the equipment. For them, it is a black box. It is still based on homogeneous condition for fluid mechanics. And what we are saying is that we can remove those assumptions and start understanding the fluid mechanics and its impact on thermodynamics, on separations, on reactions, etc. Okay, so let me just move on to an example, continuing on that example. What we did, this was about 10 years ago, one of my master's students looked at the simulation using the computational fluid dynamics as a tool to look at what the flow pattern would look like inside a single tree. And what you see here is a flow pattern of the vapor disengaging and going up, the liquid that is flowing across and overflowing over a weir. And this is a qualitative picture of the heterogeneities inside that process vessel. Okay, then we can extract quantitative information for validation purposes. That is where we need people from high fidelity experimental measurements to tell us what the flow pattern looks like so that we can validate our model. Once we do that, we have a validated model, we can then dream about newer designs using that model to see how we can predict the performance, how we can improve the performance. So here somebody measured actually the velocity profile using a fiber optic probe across the column. So we took their data and basically matched it against our prediction. So it is not a flat, uniform flow that we have assumed traditionally in the McCabe-Field kind of a method that goes into Aspen simulations, but the flow pattern is actually like this, and we can predict that if you examine in detail what happens inside. And we have worked on a number of problems over the last 30 years on multi-phase flow. Here I've just given you a sample. We worked on Gulf of Mexico oil spill. You'll see some posters in the afternoon at lunchtime. Heavy oil production with sand. We have modeled those progressive cavity pumps, gravity separation vessels, etc. But these are just examples. Let me just take a minute to identify the problem in a more generic sense. I gave you through a specific example of a distillation column. As I said, there are about 400 different types of equipment. These equipment, of course, take in energy. The energy can be coming from pumping of bubbles in here in the bubble column, fluidized bed, or energy can come from rotating impeller, or basically gravity-assisted flow, potential energy, kinetic energy, or pressure energy. So there are various types of equipment that achieve different purposes: separation, mixing, reaction. So chemical engineers basically do these three things with molecules. Take a molecule that is unwanted to produce a molecule that is wanted. Okay? So here are examples of how we go about design in a traditional sense. Even today, the chemical engineering design is taught with these kinds of empirical correlations, okay, on an equipment scale relationship for predicting the mass transfer coefficient, or predicting the rate constants or the reaction rate expressions, etc., on a macroscopic scale. Okay, so that they are, just because we are putting them in dimensional form, we assume that they become scale invariant, and that is not true because the flow pattern on which these things depend are not scale invariant. So we need to capture these processes on the dispersed phase scale, then we can scale it up and predict exactly what happens inside these black boxes. So here is an example of experimentally developed correlations for predicting the holdup in a bubble column. And as I said, you will see a bubble column outside. And I've taken the data from about 20 different publications and plotted the experimental measurements against the predictions by these correlations. And you see the data is all over. The question then to ask is this is the fundamental problem with that typical try to answer? Well, the question that you ask then is, are these experiments wrong? Are these correlations wrong? And the answer is no. The reason that they scattered all over is every experiment has been done carefully, but in a small parameter space, over a small range of flow rates, varying with surface tension over a small range, etc. And they give you a correlation that will work on that range. But if you take that and apply it in a different range, it doesn't work. But there are other correlations that have been developed in other ranges. So if you take all of them and look at the whole picture, then you get a scattered picture like this. But with CFD, resolving all the problems on the dispersed phase scale, then you superimpose on that the large-scale patterns that can develop as you scale up your equipment. We can hopefully scale up the thing with the advanced models. So that's the goal of EPIC in a broad sense. Of course, multi-phase flow is very complicated, so we need to do this for gas solid systems as a class, liquid solid systems as a class, gas liquid systems as a class. And here is an example of new thinking. Okay, so what you see here, I must thank Mike Caney from Amalgamated Research for this slide. What you're seeing is a traditional way of mixing two different streams, say a gas and liquid. Just beat the hell out of it, put some energy into it through an impeller, assuming that it will create homogeneous stuff. A new way of looking at it would be a fractal mixer. So what you see here is a pipe that is split into two and split into two, etc., all the way to very tiny configurations. And you have two streams that are coming in, blue and the red. And you are managing the large-scale structures by controlling and dividing it by yourself and bringing it together at a small scale where the molecular process can finish the process of mixing. Instead of saying, I'm going to put two pipes and put a stirrer and mix the whole thing and wait for a long time, this one says, I'm not letting nature do that, I'm going to take control of it. And if you look at nature, in our own bloodstreams, for example, these kinds of structures exist. Basically, the heart is a very efficient pump. It keeps pumping for 70, 80 years, and it does it from the arteries, bifurcating, all the way to capillaries through these fractal structures. Okay, so that kind of a new thinking should happen. So am I 2 minutes? 2 to 3 minutes. Okay. So now I'm getting into the modeling phase of it. So EPIC would like to kind of look at the modeling framework also in a very general sense. That's why we need experts from different places, different departments, etc. So current modeling occurs at the big scale, that is pilot plant scale. You have Aspen type of simulators, input the data from the pilot scale, or input the data on play efficiency from a lower level model, and you can predict the performance. Plant is typically interested in predicting the performance, controlling the performance for maximizing the profit. But what we are arguing is that if you go one level lower and look inside what happens in these process vessels, develop detailed models, you will be able to predict the parameters that are needed in the performance models. So these are the performance models, but the information needed for the performance models come in from more detailed, higher resolution models, all the way going to DNS models. You will hear something about DNS models later today. And if you go down all the way to the molecular dynamics simulations, for example. So at each level, we cut off and we say, okay, I have whatever that happens below that level, I'm not interested in modeling, so I'm going to take the experiments and put input as intermolecular potentials to the MD, then I can predict all the material properties. But if you say I'm not interested in that, I'm interested in the scopes, so the direct analytical simulation, you need to input the properties, this density, viscosity, surface tension, and you can predict models at the next scale. Then we have large dispersed phase scale, so-called volume average scale. Okay, I will end my talk with this quotation from George Box, a very famous statistician. Basically said that essentially all models are wrong, but some models are useful. And we have to keep that in mind. Modelers must keep that in mind to know that There are always approximations that we make in the model, so validation is a key part of it. To me, another less often quoted explanation from George Box is the more important one for ethic. And it basically says that for the theory-practice iteration to work, that is, how do we bring our theoretical knowledge for practical application, the models that we build, how do we apply it? For that to work, the scientist must be mentally ambidextrous. Unfortunately, I think old academics like me are not mentally ambidextrous, but the new generation of graduate students that are being trained should be mentally ambidextrous. And we try to achieve that within ethics. And how do we do that? An internship would be a great place. A person working on developing the next generation of models may want to go and spend 3 months in an experimental lab to see how they measure, what are the challenges in measuring, how he can take that data and use it in validating his model. Similarly, a guy who works entirely on tomography measurements must have an idea of where the data would be useful, why he's measuring that. And so an internship in a modeling center would be useful. So using these kinds of concepts, we can build that mental ambidexterity in the next generation of students. So I have a number of other slides that talk about more specific details, but I think I've taken enough time and laid out the big picture, and I want to keep us in time. So, is that time? Okay. So I'll be happy to answer any questions, and I think we're going into the preliminary talk next.